students, welcome to the Science 1 class. In this lesson, we shall study about properties of magnets, magnetic effect and electromagnetic induction and application of electromagnets. Is this magic, isn't it? Awesome, yes. As with the word, the magic, this phenomenon also has something to do with the M word magnet. What we have seen is no magical feat but the simple signs of magnetism. Let's try to understand the science behind it. Objects that attract magnetic materials are called magnets. Two types of magnets exist: natural magnets and artificial magnets. Naturally occurring magnets are irregular in shape and are weak. Man-made magnets or artificial magnets depending upon the applications. Artificial magnets are different shapes and sizes. For example, ball magnet, circular magnet, button type magnet and horseshoe magnet. Let's now learn the properties of magnets. A magnet has two ends called magnetic poles. Magnetic poles always exist in the past when a ball magnet is suspended freely from its center by a thread. One end of the magnet points towards the north and other end of the points to the south of the earth. At the end that points to the north is called the north pole of the magnet, and the other end which points towards the south is called the south pole of the magnet. We have seen previously that magnetic materials are attracted to a magnet. The region around the magnetic with the force of attraction can be detected is called the magnetic field. Let's understand the magnetic field and field lines with the help of the following activity. Take a small compass and a ball magnet. Note that the red end of the magnet is the north pole and the blue end is the south pole. Place the magnet on a sheet of white paper fixed on a drawing board and mark the boundary of the magnet. Place the compass near the north pole of the magnet. The south pole of the needle point towards the north pole of the magnet, and the north pole of the compass is directed away from the north pole of the magnet. Mark the position of the two ends of the compass needle. Now move the compass to a new position such that it occupies south pole occupies the position previously occupied by its north pole. In this way, proceed step by step till you reach the south pole of the magnet. Join the points marked on the paper by a smooth curve. This curve represents a field line. Repeat the same procedure and draw as many lines as you can below and above the magnet. You will get a pattern of lines. These lines represent the magnetic field around the magnet. These are known as magnetic field lines. Magnetic field is the region surrounding a magnet in which the force of the magnet can be detected. Strength of a magnetic field in degree of closeness of the magnetic field lines. They are close to at the two poles of the ball magnet. So the magnetic field is strongest at the pole. Please observe the deflection in the compass needle as you move it along a field line. the deflection increases as the needle is moved toward the pole. Magnetic field has both direction and magnitude. They emerge from North Pole and merge at the South Pole. Inside the magnet, the direction of field line is from its south pole to its north pole. Thus, the field lines are close curves to field lines across each other. Next, we move on to magnetic flux. What is magnetic flux density? Magnetic flux density is defined as a magnetic flux passing through unit area taken perpendicular to the field. B is also known as magnetic field induction. Let the flux through the area of B phi the flux through the unit area perpendicular to the field is equal to phi by the ratio of magnetic field passing through a plane perpendicular to a field, and the area of the plane is called the magnetic flux density. So magnetic flux density is equal to magnetic flux divided by area. B is equal to phi by A. Phi is equal to BA. Units. Units of magnetic flux density is meter Weber per meter squared. It is also called Tesla. The generalized formula of flux for any orientation of the plane taken in the field, let theta be the angle between magnetic field and normal to the plane with the area A as shown in the figure. The effective area of the plane perpendicular to the field is EA cos theta. The magnetic flux is given by B is equal to magnetic flux divided by effective area. This formula is used when plane makes an angle with the field, then B is equal to phi by A cos theta. The magnetic flux density is related to the magnetic field. H by magnetic flux density is equal to permeability times magnetic field, that is basically to mu. H in equation. Mu is permeability, the medium, that is material where we are measuring the fields. Next, we move on to properties of magnetic lines of force. Today we will learn about properties of magnetic field lines. The magnetic field lines have the following properties. Here you can see the picture. The magnetic lines are coming out of the North Pole and going towards the South Pole. So they are closed and continuous curves. Okay, they are continuous and they are closed curves. Outside the magnet, that is outside the magnet out, here the lines, they are directed from North Pole to South Pole. So it moves from North to South Pole. Whereas inside the magnet, they are directed from the South Pole to North Pole. So inside the magnet, it moves from South to North Pole. Okay. It means outside as from North to South Pole. That's why they are continuous curved lines. Tangent at any point on a field line gives the direction of magnetic field at that point. Suppose if it say, let's find out that you know the magnetic field strength, the direction out here at this point, let's say here, then we will draw a tangent at this point, that the tangent will be moving like this straight way. Like this, so that particular direction will be the direction of the magnetic field on this particular point. So that will be given by the tangent of the field line at the particular point. Next, they will never intersect one another. See, over here the lines will never intersect one another. If they intersect somehow, let's say that this line and the other line intersect each other, then what will happen? Then at what point there will be two directions shown by the magnetic line. Okay, because if the two lines are intersecting, that means they will be pointing out a two different direction. Okay, that means the magnetic lines, the direction will be shown different, as you know, direction which is not possible. So they will never intersect with one another, and also they are more crowded near the poles, as you can see toward the poles. Okay, both the north and south pole, the magnetic lines are more crowded. That means the strength of the magnet is moved towards the pole and far separated near the needle of the magnet. Within this portion, the middle portion of the magnetic lines are not crowded and they are very far away. So this means that the strength of the magnet is more at the poles. Okay, towards the poles, the magnetic strength is more and less at the middle of the magnet. So over here, the strength of the magnet will be less in between the poles. So the middle portion, the strength will be weaker, so that the while magnetic substances are attracted towards the magnet, they will be attracted in the poles. Thank you, students. Have a good day.